Welcome back to Computer Science Theory. This is COMS W3261, offered Summer B 2021 at Columbia University. And this is Lecture 5 on context-free languages. And I guess also on using the pumping lemma. So, as a teaser that I think I'm also going to offer in class, I want to start by asking you to think about a particular language. So, here's our teaser. Consider the language A equals 0 to the n, 1 to the n, for some n greater than or equal to 0, union with 0 to the n, 1 to the n, for any two numbers, n greater than or equal to 0, m greater than or equal to 0. So this is a language that's a union of two other languages. Sorry, this should be 0 to the n, 1 to the m. So the one language specifies our string of zeros and our string of ones has to be the same length. And we showed at the end of the last lecture that this language is non-regular. But is our whole language regular? I claim that the whole language, this union actually is regular. And to see this, we can just look at our second language here and observe that this is the language of any string of zeros of length 0 or more, followed by any string of ones. These two numbers, n and m, are independent. And in fact, the first component of the union is a subset of the second component of the union, right? If you have a string in our first language, it's also a string in our second language. So we can simplify and realize, well, wait, our language A is just equal to our second language in the union because the first language is a subset of the second, which is recognized, described by a regular expression. So A is indeed regular. That's a little brain warm up for thinking about what we thought about last time. That is non-regular languages. Before I go any further, I'll write down the announcements. So homework 3 on lectures 4 and lecture 5 is due Monday, 7/19/21 at 11:59. I know it's still tricky to keep these homeworks coming at a rate of 1 per week and to be caught up with the material, but I encourage you, even if you don't have time to do the homework until the weekend, if you have time to read it over on Tuesday or Wednesday, figure out the problems that relate to the lecture that you don't understand, and come to office hours on Thursday, Friday, Saturday. That can be a huge help when you actually sit down to solve the problems and write them up. So if you haven't been able to do that yet, I definitely encourage you to do that. And I also want to remind you that Office hours are open forums for any questions about the course. You're welcome to just come hang out. We can sit in a breakout room. You can work on the problems and listen to other people's questions. So you are definitely invited. One other announcement is that one example specifically proving 0 to the n, 1 to the n, for n greater than or equal to 0, irregular, using the pumping lemma. This example was in lecture 4 on YouTube, but in lecture 5 in class because we didn't quite get to it. So if you normally watch the class live and you come to this lecture to look for that specific example, it is in a YouTube video. It's just in the last few minutes of the previous YouTube video. So you can find that there. Other than that, they should have the same content. Readings for today. So the main topic for today is context-free grammars, which is in chapter 2.1 of Zipser. But also section 1.4, I think, is for a bunch of examples of the pumping lemma. And today our agenda will look like the following. We'll start with review. As always, we'll do more examples of proving languages non-regular. So this will be, we'll show a couple of examples using the pumping lemma, and we'll also show an example using closure properties, which it turns out you can combine with the tool of the pumping lemma to sometimes make your life easier and prove a language non-regular. So these are closure properties under regular operations, can tell you things about non-regularity of languages as well. Then we'll introduce context-free grammars, and parse trees, derivations, etc. So the basic concepts that have to do with context-free grammars. Also context-free languages. So context-free grammars are going to be sort of like regular expressions in that there'll be ways to succinctly describe and generate strings in a language, but it's going to turn out that they can generate a much larger class of languages than the regular languages that we'll call the context-free languages. So look forward to getting to that because we're about to get a ton more power in our universe of languages, expand our horizons a little bit. All right. So last lecture, we finished our proof that a language is regular if and only if some regular expression recognized it. So we now know that a language is regular if and only if some Dfa recognizes it. And this is by definition, this is how we define the regular languages. Also, if and only if some Nfa recognizes it. And this is because we showed how to go from an NFA to a DFA and vice versa. The backwards arrow was trivial because DFAs, at least DFA state diagrams, are also NFA state diagrams. And then if and only if some regular expression evaluates to that language. And we proved this by showing that a regular expression can be converted to an equivalent NFA using our inductive definition of regular expressions and closure properties. That was the one direction. And then we also showed that a regular language, which is recognized by some DFA, our DFAs can always be converted to a new thing called a Gnfa, a complicated automaton with some special rules that labels its transitions with regular expressions. And then Gnfas can be boiled down to regular expressions. So we can go backwards and forwards between regular expressions and regular languages. So that was one thing we did. We introduced this thing called the Gnfa that we used as an intermediate step in our proof. So Gnfas are like NFAs, but transition on regular expressions. They have some special properties. They have exactly one start state, Q start, and one accept state, Q accept. They have exactly one transition between every pair of states in, well, I'll write it in symbols actually, because it'll be good review. In the domain Q, set minus Q accept, Cartesian product, or cross Q set minus Q start. That is, for every pair of states in our Gnfa, which we can make by drawing one state from Q and one state from Q, accepting transitions going out of the accept state or transitions going into the start state, and also including pairs of the same state repeated twice. Any pair in this set has exactly one transition between them. We showed how to convert DFAs to Gnfas by adding states and adding null edges. So these are edges where you transition on the empty language. No strings match that regular expression. There are no strings in the empty language, so these are just dummy edges that we use to make sure our Gnfas meet our definition. And finally, we showed how to boil down a Gnfa to a regular expression by iteratively ripping out states. That is, we said if you have any two states, Q1 and Q2, and a state QRIP you'd like to remove, then you can consider all the regular expressions labeling the states that some computational path might take to get from Q1 to Q2 through QRIP. So this is just a little gadget. It's not a whole GNFA, it's just one little part of a GNFA. I'm considering some state that I've designated as QRIP that I want to take out, and two other states, Q1 and Q2. And I'm observing if I just consider every possible computational path that might go from Q1 to Q2 through QRIP, that can be summarized by the regular expression R4 union R1, R2 star, that is, we go around the loop to QRIP, from QRIP to itself a certain number of times, and R3. So our ripping claim was that for every pair of states that looked like this in a little subgadget, we could replace the edge between them with this new regular expression and effectively remove QRIP from our GNFA. So that summarizes the big old proof we did the other day, this DFA to regular expression proof. We showed how to convert a DFA to this strange new automaton, the GNFA, and then ripped out the states of the GNFA one by one to get a regular expression. And then we moved on from regular languages entirely. In particular, we introduced something called the pumping lemma. So if you remember, this was a technical lemma with several conditions, and effectively it says all regular languages have this specific technical property. So if we want to prove that a language is not regular, one way we can do it is by saying, well, let's assume it is regular. Then the pumping lemma must apply. But that assumption leads to a contradiction. The pumping lemma doesn't apply, and therefore this language cannot be regular. That's how we're using this tool and what this tool is. I'll rewrite it for you because we're going to want to have reference to these particular conditions. So the pumping lemma says, if A is a regular language, there is some pumping length P such that every string S in our language that's long enough, that is, every string in our language that has length at least P can be divided into 3 substrings, X, Y, and Z, satisfying X times Y repeated I times, X concatenated with Y repeated I times concatenated with Z is always in the language for every I greater than or equal to 0. The length of Y is non-zero, so Y actually has some symbols in it, and the length XY is at most P. And if you remember, intuition behind this was loopiness. We proved this lemma by saying, suppose we have some DFA and there's some computational path through the DFA. If that computational path is long enough, then it must visit some state twice. And if we visit some state twice, then we have a loop. So our string X, the idea was it was the sequence of symbols that took us to the beginning of the loop. Y was the sequence of symbols that took us around the loop. And Z was the sequence of symbols that took us to the accept state. Our first condition holds because no matter how many times we go around this loop, we still have a string that's in the language because we've identified a computational path. X, Y, 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 Z is just a string that goes around the loop Y 5 times. Y is greater than or equal to 0 because it's a loop. We don't want Y to just be the empty string. And X, Y is less than or equal to P because we have to get to a loop before we have seen P states, where P is the number of states in the DFA. We definitely will see a loop by the time we've seen every state. We've seen a number of states equal to the number of states in the DFA. So that's our pumping lemma, and that's our intuition again. So because proofs using the pumping lemma are a little bit tricky, they require keeping careful track of what we're doing in the cases we're keeping track of. I want to give you a couple more of them. It's also a good chance to slow down and think about our proofs, to do examples of proofs, which I know are a core feature of this class and show up in the homework over and over. I've had a few questions during office hours of how do I write a proof that is complete and convincing? The short answer is that any person who knows the relevant mathematical concepts should be able to read your proof and say, either that proof is fully rigorous, it covers every case and tells me exactly what I need to know, or it's at most a half step away from fully rigorous. It's very clear. With no extra intuition or thought on my part, I should be able to see how to make your proof be fully rigorous and cover every case. So, it might occasionally be okay to say, we do this for the string of all zeros, and for the string of all ones, we do the exact same thing, replacing 0 in the first proof with 1 in the second. But generally, full, complete proofs. So here's an example using the pumping lemma. Suppose we want to show that the language F such that F is WW, where W is a particular string over the alphabet 0, 1 star. Let's just write 0, 1 star for sigma, is non-regular. If you saw this language just out in the wild, you didn't know whether it was regular or not, you might observe that to check if a string is in the language, we have to somehow check if the string is 2 strings repeated, which seems like we would need an arbitrary amount of memory. We don't know how long this string W is, so it seems like we might need to remember the first string W and then check it against the second string W. The fact that that operation seems like it might take an arbitrary amount of memory is a good indication that this language might be non-regular. Our intuition is not perfect, but we can certainly then go from there and try to prove it using the pumping lemma. So, proof. First step of a proof using the pumping lemma is always going to be assume for contradiction that F is regular. So by our assumption, if f is regular, thus f satisfies the pumping lemma and there exists a pumping length P such that any string S in F with the length of S greater than or equal to P can be divided into substrings S equals XYZ such that, what were our conditions? Y is greater than 0. Length of XY is at most P. And X, Y to the I, Z is in the language F for all I greater than 0, greater than or equal to 0. So all I've done here in step 2 is I've essentially written down precisely what the pumping lemma tells us. So I didn't even need to memorize the pumping lemma to do this. I could have just written down assume for contradiction that f is regular and written down step 2 from reading off the lemma. It's a thing I could do if the technical condition still is not very intuitive to me. And now we want to find a contradiction. So to find a contradiction, we need to identify some string S of length at least P such that this condition doesn't hold. And then show that no matter how we divide S into pieces, these conditions don't hold. The trickiest part of these proofs is always going to be choosing S. So for simple languages, there are often usually only a few strings you can choose, and most of them will work. But the trick, the creative spark here, is usually picking a string S that somehow captures the non-regularity of the language. And in this case, the non-regular feature is that we might have 2 arbitrarily long strings that must be the same. And we'll consider the string S equals 0 to the P, 1, 0 to the P, 1. This might seem like a weird choice, but it's actually one of the simpler strings that meets my requirements. So for instance, if I'd set S to be 0 to the P, 0 to the P, that is a very simple string repeated twice. This string doesn't seem to really capture the non-regularity of the language because this is just 0 to the 2P. And there's not really any counting required. If I see a string of all zeros of even length, then I know it is in this language. This isn't really a hard string. So I need a slightly harder one. Maybe it could be 0, 1 repeated many times. Well, no, I still don't want to do one symbol. So in this case, when I picked S, I've tried to choose a string that meets the requirements of the language and seems to require counting. I need to count at least P zeros coming before a 1 and then match that again. So that's why I picked this string. And this string will work, but if you were doing this proof on your own, it would be totally reasonable to test out a couple of different ones and try to figure out one that worked for you. So we'll say, by assumption, xy is less than or equal to p. So if we could divide this string, we would know that xy would be less than or equal to p. And this is going to tell us that the last part of our string all has to be in the substring z. So thus, the length of Z is at least 2p plus 2. That's the total length of the string, minus p equals p plus 2. As a result, Z contains the substring 1, 0p, 1. So effectively what I've done here is I've said, well, this string is long enough that by our assumption, X and Y both have to occur in the first p zeros. Z has all the rest of the characters. So it has the substring 0, 1, 0 to the p1. Thus, Y consists of all zeros and XYYZ equals, well, it has XY, and then it has Z. So it definitely starts with 0 to the P and ends with 1, 0 to the P1. But it's also got another string Y in the middle, made up of all zeros. So if I concatenate that with my first string of zeros, I've repeated my Y string. So I've got length of Y extra zeros. However, X, Y, Y, Z is not in the language F because the length of Y is greater than 0 by assumption. So this string can't be divided into identical substrings of equal length. So I've done what I'm going to do most of the time when I use the pumping lemma, which is write down my string S, use my two additional conditions, y greater than or 0, xy is less than or equal to p if I have to, because that'll reduce my possible ways of dividing my string. And then I'll observe, often with multiple cases, but sometimes not, that xyz or xy to the 10th z or xy to the 0z, which is just xz, is not in the language. So my third condition fails. Thus, S cannot be pumped. And by cannot be pumped, I mean can't be divided in such a way that it satisfies these conditions. F does not satisfy the pumping lemma, and thus F is non-regular. Great. I'm going to do one more, just because it shows another creative way we can choose a substring S. Of course, if you're super confident with the pumping lemma at this point, feel free to fast forward 10 minutes. So here's another example of the pumping lemma. We'll show that the language D equals 1 to the n squared for some n greater than or equal to 0 is non-regular. So D is a unary language, meaning that it's a language of strings over an alphabet that has only one symbol. It's just a language of ones. And it's going to be all the strings made out of ones that have a length that's a square number. So not all the strings of ones. It'll be the string of 1, 1, of 4 ones, of 9 ones, of 16 ones, etc. So to prove this, using the pumping lemma, as always, we'll assume D is regular. So therefore, by assumption, D satisfies the pumping lemma. So there exists a pumping length P such that for all S in D with the length of S, at least the pumping length, S can be divided into X, Y, Z, satisfying Y is greater than 0, XY is less than or equal to P, and X to the YIZ is in the language for all I. So I'm writing the pumping lemma over and over. The more times you write it, the more clearly it sticks into your brain. So let's see, now we need to choose some string, some long string that can't be pumped. I could choose 1 to the P, but if P is not a square number, then that string won't be in the language. So I would say the most reasonable choice, probably the choice you would try first if you were experimenting, is this string. Let's choose the string W equals 1 to the P squared. P squared is definitely bigger than P, so this satisfies the condition that W has length at least P. What we'd like to show is that when we pump this string, we get a string that's not in the language. And intuitively, this should make some sense because most numbers are not square numbers. So when we pump this string, we'll get a lot of strings of different length, and most of those lengths should not be square numbers. So most of those strings should not be in the language. So suppose we divide W into X, Y, Z such that X, Y is at most P and Y is non-zero. Now, we're going to do some reasoning about the length of these strings that get pumped, like we said we would. We know that the length of X, Y, Z is just the length of W, because they're the same string, is just P squared. By definition, that's what W is. It's the string of P squared ones. X, Y, Y, Z equals the length of X, Y, Z plus the length of Y, because these are just some strings concatenated together. The length of X, Y, Z we already know is P squared plus Y is greater than P squared, as the length of Y is greater than 0. So what we've shown in this line is we've essentially said, consider the string where we repeat the substring Y twice. It's got to be longer than X, Y, Z because Y is non-zero, which means it can't have length P squared. So that's a good start. We know it's longer than P squared. We want to make sure that its length is not some other squared number. And to do that, we can show it's less than P plus 1 squared. So in particular, we know P squared plus the length of y is less than or equal to p squared plus the length of xy, because that's just x and y concatenated. So the total length is the length of y plus the length of x. But we have an upper bound on the length of xy, right? We've said xy can't be any larger than p. So this is less than p squared plus p, which of course is strictly less than p squared plus 2p plus 1, which is p plus 1 squared. So what we've just shown is based on our requirements for the length of x and y, we have p squared is less than the length of x, y, y, z is less than p plus 1 squared. So the length of x, y, y, z is not a perfect square. Thus, x, y, y, z is not in the language D, because our requirement for being in the language D is that the length of the string was a perfect square. So it's another tricky way of proving a language non-regular that required we use our other assumptions about the length of x, y, and the length of y. So D fails the pumping lemma. Because it has some string that cannot be pumped that's sufficiently long, and thus D is non-regular. Now, I'm going to show you one last example, and this one will prove that a language is non-regular without directly using the pumping lemma. It's another proof kind of by bootstrapping previous concepts we already know using the regular operations. So in particular, let me show you what I mean. So example, let's show 0 to the n, 1 to the n, for n greater than or equal to 3 is non-regular. So this is very simple, or sorry, very similar to a language we saw earlier that was 0 to the n, 1 to the n for any n greater than or equal to 0. We proved that was non-regular using the pumping lemma, and I claim we could do the exact same for this language if we wanted to. The same string might even work as long as the pumping length is greater than 3. So we could certainly prove this language non-regular that way. But there's another way to prove this language non-regular that uses closure properties. In particular, we know, because we already proved, that 0 to the n, 1 to the n, such that n is greater than or equal to 0 is non-regular. We observe that 0 to the n, 1 to the n, such that n is greater than or equal to 0 is equal to the union of the current language we're considering and another language right? So I've just observed that the language I want to prove is non-regular. The union of it and some other language is a non-regular language. And in particular, 0 to the n, 1 to the n, such that n is less than 3. Well, that's just the language containing the empty string, the string 0, 1, and the string 0, 0, 1, 1. That's also a regular language. because it's finite. As we mentioned last lecture, all of the finite languages are regular. The reason about that, you can just observe that we could write down simple Dfas for each of the individual strings and then use closure under union to show that the whole finite language is closed or is regular. So, okay, I've set up this interesting equality that the union of a regular language and our target language is a non-regular language. And I claim this shows that our target language is non-regular. If 0 to the n, 1 to the n, such that n is greater than 3, is regular, then its union with 0 to the n, 1 to the n, such that n is less than 3 is regular by the closure of regular languages under union. This is a contradiction. This is a contradiction because we already know that the union of these two languages is non-regular. So our target language is non-regular. So we were able to show that this language was non-regular by showing that its union with a regular language was non-regular. And this trick will work for all of the regular operations. So any operation that we've shown that the regular languages are closed under, if I know that my target language concatenated with a regular language is non-regular, then my target language can't be regular. Because if it were, then concatenating with a regular language would yield a regular language by closure under concatenation. So this is another type of proof. Again, you could have just used the pumping lemma in this case, but this took a little less work. And it's another way to cleverly use something we already know. So it's good to have in your back pocket. So at this point, we will end this segment of the lecture. When we come back, we'll talk about context-free grammars and new ways of generating bigger and better languages. So thanks for watching. See you in the next part. Bye.